In a quiet room filled with humming machines, a team of scientists presses run. On the screen, darkness flickers, then light appears. Galaxies begin to form. Stars ignite. Gravity bends space. But this universe isn't real. It exists entirely inside a supercomputer. So here's the question. How can lines of code recreate the birth and evolution of the cosmos? Welcome to the quantum classroom. The universe is too vast to experiment on. We cannot rewind it. We cannot rerun the Big Bang. We cannot move galaxies like chess pieces. And yet, scientists do something astonishing. They recreate the universe inside a computer. Computational astrophysics is the science of using mathematical models and powerful computers to simulate cosmic phenomena. Instead of observing passively, scientists build virtual universes governed by physics and watch them evolve. But why is this necessary? Because much of astrophysics deals with events that unfold over billions of years. A galaxy forms over timescales far beyond human life. A star's birth takes millions of years. Even gravitational interactions between galaxy clusters evolve slowly. So if we can't wait billions of years, we simulate. At its core, computational astrophysics begins with equations. The universe follows physical laws: gravity, thermodynamics, electromagnetism, nuclear fusion. These laws are written in mathematical form. But here's the challenge: the equations that describe cosmic systems are often too complex to solve exactly. Take gravity. If two objects interact gravitationally, the math is manageable. But if you simulate a galaxy with billions of stars, each influencing every other star, the equations explode in complexity. This is known as the n-body problem. It cannot be solved neatly. It must be approximated. And that's where computation enters. Supercomputers break space into small pieces, divide time into tiny steps, and calculate how each piece evolves moment by moment. Imagine slicing the universe into a three-dimensional grid and asking, at each point, what is happening here? Is matter collapsing? Is gas cooling? Is gravity pulling inward? Now multiply that by trillions of calculations per second. The result is a dynamic model of cosmic evolution. But simulations are not just visualizations. They are experiments. In a laboratory, you might mix chemicals to test a hypothesis. In computational astrophysics, you adjust parameters. Increase dark matter density. Change the rate of star formation. Modify initial temperature fluctuations. Then you press run. If the simulated universe matches what telescopes observe, your theory gains credibility. If it doesn't, something in your understanding is incomplete. This is how we study dark matter. We cannot see dark matter directly. But when scientists simulate a universe without it, galaxies fail to form properly. Structures remain too smooth. Clusters do not emerge the way we observe them. Add dark matter, invisible mass that interacts gravitationally, and suddenly the cosmic web appears. Filaments stretch across space. Galaxies cluster naturally. The simulation behaves like the real universe. Computational astrophysics has revealed that the large-scale structure of the universe resembles a vast cosmic web. Galaxies are not randomly scattered. They sit along filaments of dark matter, like cities connected by invisible highways. This insight did not come from observation alone. It emerged when simulations aligned with telescope surveys. But building these simulations is not simple. Space is continuous. Computers are discrete. That means reality must be approximated. Scientists use numerical methods to translate smooth physical laws into step-by-step calculations. Every approximation introduces potential error. So how do we trust the results? Through validation. Simulations are constantly compared with real astronomical data from the Hubble Space Telescope, the James Webb Space Telescope, radio observatories, and cosmic microwave background measurements. If a model predicts galaxy distributions that match observed surveys, confidence grows. If it predicts star formation rates incorrectly, it must be refined. Computational astrophysics is a conversation between theory, simulation, and observation. And it has transformed modern astronomy. Consider black holes. We cannot watch matter fall into a black hole in real time. But simulations allow scientists to model accretion disks, swirling gas heated to extreme temperatures. They calculate how magnetic fields twist, how jets launch at near light speed. In 2019, when the first image of a black hole was released, it closely matched simulation predictions developed years earlier. The image validated decades of computational modeling. This is the power of predictive science. Today's simulations are run on some of the most powerful supercomputers on Earth. These machines contain hundreds of thousands of processors working in parallel. They perform quadrillions of calculations per second. Even then, compromises are necessary. A full simulation of every star in a galaxy with atomic-level precision is impossible. Instead, scientists use subgrid models. These are simplified representations of processes too small to resolve directly, like how gas clouds collapse into stars. Think of it like modeling weather. You cannot simulate every air molecule in a hurricane. But you can model pressure systems and temperature flows accurately enough to predict behavior. Astrophysics works the same way. And the field continues to evolve. Machine learning is now assisting simulations. Artificial intelligence can identify patterns in massive datasets, optimize parameters, and accelerate computation. AI does not replace physics, it enhances it. At the same time, simulations are becoming more detailed. Modern models incorporate magnetic fields, radiation transport, cosmic rays, and relativistic effects. The universe inside the computer is becoming more realistic with every generation. But perhaps the most profound aspect of computational astrophysics is philosophical. For the first time in history, humanity can create universes governed by the same laws as our own and watch them unfold. We can test what happens if the density of matter changes slightly. We can explore how galaxies would form under different initial conditions. We can probe questions that would otherwise remain forever theoretical. It changes our relationship with the cosmos. Instead of being passive observers, we become investigators inside a digital laboratory of reality. Yet it is important to remain grounded. Simulations are tools. They are only as good as the assumptions built into them. They do not prove truth, they test consistency. They guide inquiry, but they do not replace observation. The real universe remains the final authority. Still, computational astrophysics represents one of the most powerful scientific revolutions of our time. It bridges mathematics, physics, and computer science. It transforms equations into evolving galaxies. It compresses billions of years into hours of runtime. And perhaps most importantly, it allows us to ask better questions. What shaped the cosmic web? How do supermassive black holes influence galaxy evolution? Why does dark energy accelerate expansion? Some answers will emerge from telescopes. Others will emerge from code. In the quiet hum of supercomputers, miniature universes are born, evolve, and fade, not as fantasy, but as structured explorations of physical law. And as computational power grows, so does our ability to understand the cosmos. The universe may be vast beyond imagination. But through computation, we have learned to hold a version of it in memory. And that may be one of humanity's greatest scientific achievements. If you want to explore how physics, computation, and cosmology are shaping the future of science, continue your journey with the Quantum Classroom, where curiosity meets evidence.